Okay. Oh yeah. All right. All right. Okay. So is it now loud? Okay. So yesterday we talked about these matrix elements S sub L, and I was relating L to a particular impact parameter. So starting from 0 would be almost like a central, and then when you increase L, it goes outside. So now we can put it all together, and we can actually study the nucleus with a code or some kind of numerical study. So, and this is what's illustrated here. So this is an example of these SL matrix elements showing both their real and imaginary parts as a function of this partial wave L. Okay. So this is the behavior, and you see that when L is low, so then essentially here for low L's we have real and imaginary part nearly at 0. So real part, so the S matrix is nearly at 0, which means that what happens is you have initial wave in a given partial wave L, and then nothing comes out. Okay, so that would mean 0, because remember, S matrix is the matrix that relates your initial wave function to a final wave function. So if nothing comes out, you have pretty much an absorption, complete absorption. So this would be the case of a complete absorption, and that's kind of logical. If you have a big nucleus, you shoot something in, then everything gets absorbed up to a certain, up to you start reaching the edge. So once you reach the edge, which is here, the real part quickly increases to 1. And by the way, far away for a very high partial wave, what would you expect? So what the S matrix element should be for a partial wave which is very high? So what would you expect if no scattering happens? So your initial wave is the same as the final wave, right? So it means the matrix element relating them to is what? 1. Okay, so it's a real number 1. Nothing happened. All right, so therefore far away, you expect this to be 1 and the imaginary part to be 0. Okay, so, and this is indeed what happens. So far away, you're essentially missing. Your impact parameter is so large that you just miss. I mean, you're just going far away. Okay, so, and then here something happens, and of course here is probably the most interesting picture, because this is what happens on the surface here. So you have some absorption, and then the real part increases. So this is an example. Of course, this calculation, since there is an absorption, implies that you have a complex potential. So this looks like a semi-transparent drop, which is completely non-transparent in the middle, and at the edges you see some effect. So you can even consider it from a classical perspective. So therefore, these kind of studies are called optical model studies, because it looks like an optical model. So in this optical model, you have a potential, and the potential is often modeled with so-called the Wood-Saxon potential, and I hope you have heard about it. It looks simply almost similar to an inverted Fermi distribution. So it's a smooth potential. I can give you essentially a drawing of this potential. So this would be like this potential here. Both real and imaginary parts of this shape, and this can model some reactions. Now, in terms of the codes, by the way, I should mention that there is a very good code in Fresco where you can easily obtain these results, and it has even different kinds of parameterizations for various nuclei where you can just put in and obtain this plot. Okay, so this is what I wanted to say in relation to what I have done yesterday. So now I would like to continue. I didn't want to discuss the astrophysics here. I want to continue the discussion of identical particles. So for identical particles, we talked yesterday about the proton and neutron, and this discussion of scattering at low energy for proton and neutron is extremely important. because that lets us learn about nucleon-nucleon forces. And as I was also mentioning yesterday, that once you have nucleon-nucleon forces, you can start building our understanding about heavier nuclei. You can take computers, put in together the nucleon-nucleon forces, and try to understand what happens heavier. And this road is very complicated. In particular, one issue which is complicated, that you are sort of trying to do an inverse scattering problem. So from scattering observables, you are trying to determine what is your potential. So, and this path is not necessarily unique, however, sometimes or often, it actually doesn't matter what is the exact form of your potential. What matters is that all observables are correctly reproduced. So anyway, we talked about proton-neutron yesterday, and of course now I have to mention other possibilities, such as identical particles, which I'll try to do briefly because this is an important component of scattering theory. So what happens if the particles are identical? So if the particles are identical, such as neutron-neutron or proton-proton, then obviously you have an issue that you don't know which one is which. And this figure illustrates you sort of an idea of classical situation, that you can have actually two different scatterings, even classically. You can scatter at angle theta, and you can also scatter at the angle of pi minus theta, which is shown here. And both of these will count by your detector. So, and since particles are identical, you do not know which you have. I mean, you have both. So you cannot distinguish one from another one. So in order to know these, you have to actually call particle A and B, but you are not allowed to do that. So therefore, classically speaking, you're just going to sum two cross sections. So you're, in the classical terms, for identical particles, so you would have your d sigma as being a sum for d sigma for the angle theta plus d sigma for the angle pi minus theta. So that's going to add up. And of course, if you divide by d omega, then you have the same thing. What is interesting that for pi over 2, so d sigma over d omega for pi over 2 would be essentially d sigma over d omega for the same independent particles, because you get them twice, right? Yes. Which one? In here or in here? Yeah, there should be minus. Sorry. Yes, yes. Okay. It's typo. Okay, so yes, that's right. They're both inverted. Okay, so now what happens in quantum mechanics? So in quantum mechanics, you have to obviously for this discussion, you have to have discussion for either bosons or fermions, because then there is a distinction here. So you have to have a symmetrized or anti-symmetrized wave function. So I'm going to skip all the big details about how do you deal with the spin, but the idea is that spin is an extra variable. So therefore, you have essentially two choices for your coordinate variable. So your coordinate variable has to be symmetric or anti-symmetric. So in the simplest case, so this was classical. Now in quantum mechanics, in quantum mechanics, you have to have your scattering function, and the scattering function originally was e to the I kr, as we wrote yesterday, plus f of theta e to the I kr over r. It's spherical. So this was our wave function that we started yesterday. Now, for identical particles, you have to symmetrize here when you exchange, and this is relative coordinates. So when you have two particles and you exchange them, then exchange means you change the sign of r to minus r. So therefore your wave function now, so this is independent. Now for identical, you would have 1 over the square root of 2, and then here you have e to the I k dot r plus or minus e to the minus I k dot r. And then you would have here plus also 1 over the square root of 2. And here you have f of theta plus f of pi minus theta e to the I k r over r. Remember that this is spherical, so this was a vector, therefore it changes sign. This is a spherical, that it doesn't change sign. Okay, so this is now a new scattering amplitude that you have to consider, again, plus or minus here, depending on symmetric or anti-symmetric. So then your initial flux is 1 over the square root of this IKR incoming. And then in the outgoing wave, you have 1 over the square root of 2 and this combination. So therefore, repeating exactly the same steps as we have done yesterday and the day before yesterday, we can obtain now the scattering cross-section with exact same steps. So our scattering cross-section is going to be initial flux here, which is initial current 1 over the square root of 2, but square that gives 1/2. And then in here I have the same 1/2, which will cancel out, and this is my new scattering amplitude. So therefore, this is just going to be f of theta plus minus f of pi minus theta squared, depending on the symmetry, right? So this is just a modification that I only have to do in order to describe the scattering of identical particles. And now there are various combinations, obviously. So for bosons, I would just have to use plus sign, spinless bosons. Now for fermions, if I consider, let's say, 2 neutrons, then there is a question, what about the spin variable? So the 2 neutrons, as we talked, can be spin singlet or spin triplet, right? So if they are spin triplet, then it means that they have spin 1. So 2 spin 1s are aligned, so it means this is an aligned state, so it means it's symmetric in the spin space. So therefore, in the spatial part, it has to be anti-symmetric. So for Nn, for example, if the spin, total spin is 1, then this is symmetric, so therefore d sigma over d omega has to be anti-symmetric, so therefore I have to take f of theta minus f of pi minus theta. Right. So similarly, of course, if this is singlet, if this is 0, then I would have to take d sigma over d omega equals to, with a plus sign, f of theta plus f of pi minus theta. Okay, so then again, we can start comparing with the classical situation. An interesting case happens is, what if what if I'm looking at the scattering at 90 degrees at pi over 2? So at pi over 2, this, so for pi at theta equals pi over 2, then for s equals 1, I just have 0. Right, so d sigma over d omega is going to give me 0. For s equals 0, this is going to give me 2 times, so it's going to be d sigma over d omega equals to 4 magnitude f of theta squared. Okay, so, and now of course one more question is just to generalize this idea. So what happens if I cannot measure spin? So if I'm just scattering and I don't know what the spin is. So if I cannot detect, or I create my beams which are completely unpolarized, then what happens? Yes, then I have to average. So, and the question is, how do I average? So each spin projection is equally possible. There are 4 different combinations that I can make with spin up and down. So I can have both up, both down, and down, up. So there are 4 total combinations. Now, in terms of coupled, triplet is 3 combinations, and singlet is 1. So therefore, I will get for unpolarized d sigma over d omega, so this is unpolarized, I will have 3/4 of d sigma over d omega for s equals 1. So this is s equals 1 case, and this s equals 0 case, plus 1/4 of d sigma over d omega for s equals 0. Right, so, and of course for 90 degrees, I will have, this one is 0, so the 3/4 one is 0, and this 4 cancels out, so I'm actually going to get 1. So for theta equals pi over 2 d sigma over d omega, unpolarized is just a magnitude of f squared. Okay, so this is the general idea about this, and of course once you have this interference, then you have, usually the plots have a symmetric shape once you square it, and then you also have an interference between your scattering amplitude for theta and pi minus theta. Okay, so this is one part that's necessary, and then there is another part which we haven't discussed haven't discussed enough, is the Coulomb. So now if I have 2 protons, then there is another problem, is that I have to add Coulomb interaction. So for Coulomb interaction, let me see if I have my where? So in here. So in here, 3/4. But this is for a particular angle, pi over 2. So when, okay, so this is a general answer here, d sigma, and you agree with that one. Okay, so now let's consider a particular case when angle is pi over 2. Then this is 0, so I'm going to put 0 in here. And then this is just 1/4 of that, right? Yeah, it should be theta of pi over 2, obviously. So this is a particular example. All right, so now going to another part which I should mention is a Coulomb component, because if you scatter 2 protons trying to understand nucleon-nucleon forces, then you have to include Coulomb. In fact, in most scatterings, Coulomb is extremely important. So what did we have last time? So last time we discussed how do I derive that Wronskian, and then in order to add Coulomb, I just have to add 1 over r interaction. So let me briefly remind you what we had yesterday. So we had, for radial wave function, du squared over dx squared, and the x was kr. minus. Here I had plus L times L plus 1 over x squared. That's the centrifugal part. And then now I will, times U. Now I will add Coulomb. So now recall, how did we get to this? Well, so let me just leave a space for Coulomb and say that this is equal to 1U, right? So, and again, talking about free space. So this U is right now for free space. So for Coulomb, we have E squared Z1, Z2, and then over R. Then in order to obtain this equation, we had to multiply everything by h bar. So we had to multiply by 2m over h bar, k squared h bar squared, right? That's how we obtained this equation. So then you look at this term, and this term is essentially can be written as 2 some constant eta over x. Okay, so, and this constant eta is what I am after. So this eta is called a Coulomb parameter, a Sommerfeld parameter. From here, you see that this is E squared Z1 Z2 over h bar squared k squared times the mass. Yes, only 1k, because 1k went to this kr to make it x, yes. Okay, so this is my parameter, and if you look at this equation, every term in this equation is unitless. So therefore, of course, this parameter has to be unitless. And why I'm drawing attention to this parameter, because that defines the strength of our Coulomb interaction. So everything in Coulomb interaction would depend on this parameter. Okay, so now how do you evaluate this parameter? In fact, again, yesterday I had some question, how do I know what momentum k is small, or wave vector is small or big? How do we know that? So perhaps because of that question, it's worth addressing how do we deal even with units in nuclear physics and in nuclear reactions. So let's say my k, let's just do units first. So what is k small or big? So my wave vector in scattering that I was discussing, and I'm discussing still right now, I'm talking about a very large wavelength. So my so in a sense, my k is a small number. So how do I know if it's small or big? So suppose I have, I would like to evaluate the energy for a particular k. So what's the steps in evaluation? I have h bar squared k squared over 2m, right? And let's say I have k as 1 in inverse femtometer. So it's in the units of femtometers minus 1, right? So how do I evaluate what is the energy that would correspond to this if this is the mass of a nucleon, just approximately. So again, the way in nuclear physics we do these kind of evaluations through this very important constant. So if I take h bar squared multiplied by c squared, then I have here my k squared, and then I would have 2mc squared. So this h bar c is a very important quantity because it is 197 MeV femtometers. And that lets you evaluate everything because this becomes then, your energy is 197 squared times the k that I want, which is 1, and let me write it, times 1 divided by twice the mass of the nucleon, which I'm just going to put 1000 MeV. So the units here are 197, this is MeV squared, femtometers squared, times 1 squared, so this is 1 over femtometers squared. And then this is going to be 1000 MeV, so I'm having MeV. So you see femtometers cancel, and I have MEV correctly, right? Numerically, this is about 20, so this is about 40 over 2, so this is about 20 MeV. Okay, so these are the steps of evaluation. Okay, so when I'm dealing with Coulomb, I have to have the same ideas, and the same ideas are as follows. There is a fine structure constant, so I will separate E squared over H bar C. So I had used one H bar. I will need C here times M over H bar K left, right? The important part is that E squared over H bar C is also unitless, and it's fine structure constant, so this is called alpha equals E squared over H bar C, and it's numerically about 1 over 137. And of course I should add here Z1, Z2. So altogether then, this Sommerfeld parameter, actually it's exactly equal so far, is alpha. Then if you see this, this is speed of light, this is H bar K. H bar K is momentum, but it's non-relativistic momentum. So you can write it as momentum divided by mass is the velocity, so it's C divided by the velocity times Z1, Z2. Okay, so, and you happily find out that this is, of course, has no units, as it's supposed to. Now, I don't like writing here, you can say V over C is beta, but it's non-relativistic expression because I used non-relativistic, so writing beta would be completely misleading in this particular case. Okay, so this is how you would evaluate this quantity. And now you see another important part is that for Coulomb interaction, your strength is 1 over V. So the slower your speed, scattering, the more important Coulomb is. And it's proportional, of course, to a product of charges. So these are key elements about Coulomb. Now, Coulomb problem can be solved completely. And exactly. So there are Coulomb functions, again f, which is far away proportional to sine of x. Then we had minus pi L over 2 as before, and then we have plus, I believe, eta logarithm of 2x, and then plus phase shift for a particular L. Let me just verify that this is, actually it's minus here. Okay, so this is minus. Okay, so this is f function, and then the similar function is g function, which is just a cosine of the same thing. Okay, so now as I was alluding before, of course, the problem with these functions is that if you try to evaluate them relative to a typical sines and cosines, so yesterday we had just x minus pi L over 2. Then this is the phase shift, but this phase shift would depend on x. So in the sense of a plane wave, you never have a plane wave with Coulomb interaction, because Coulomb interaction is long range. So you start feeling the potential infinitely far away. Okay. So then there is this issue of this phase shift L. So, and the phase shift L is given by the argument of the gamma function. So delta L is argument of the complex gamma function of gamma 1 plus L plus I eta. So this is an argument of the gamma function, and again it can be numerically evaluated, and the gamma function is like a factorial. So in fact, if you know delta 0, then you can evaluate every next delta L, because each time you need to add an integer number, then it's like a factorial if you have, so classically gamma of 1 plus n is n factorial. So if you increase n, and then you just multiply by each time by n, and you go recursively. Okay. Then for delta 0 is of course important, and you have to evaluate that numerically. And here is also an important difference from the scattering that we have discussed before, that delta 0 actually behaves very differently, behaves exponentially. So this is at e to the minus 2 pi eta. So that's the behavior of delta 0 at very low energies. And this exponential behavior is related to, if you look at it as scattering, then in the scattering process, if you have a Coulomb potential, you need to penetrate inside the potential. And then if it's a full scattering, then you need to go back, because it's a twice, I mean, phase shift is 2 delta. So you have it going twice, and therefore this is related to a tunneling probability, and that's why it becomes exponentially small. So this is a tunneling problem. Okay, so now finally, I guess, with the Coulomb problem, when you put it all together, when you start evaluating Coulomb problem, then you evaluate your, so in our, again, scattering equations, so we had so we had our scattering was scattering amplitude f of theta was 1 over 2 ik sum over L 2L plus 1 PL, and here we had S minus 1. So this was our scattering amplitude. So this S minus 1, in case of a Coulomb problem, you will evaluate this, you have a change, this S matrix is 2I, and here you have delta Coulomb plus delta nuclear. So if you have an additional interaction, so in this case I didn't write any additional interaction, but if you have an additional potential, then this potential will lead to an extra phase shift, which you will evaluate, because you will evaluate U in the form of F cosine delta nuclear plus G sine delta nuclear, right? So you will have this term, and you will have an additional nuclear term. Okay, so this is now your scattering. If you don't have any nuclear interaction, then you will have a Coulomb scattering, which will just be defined by these phase shifts for Coulomb only. Okay, so, and this is of course minus 1 then. So then once you evaluate this total phase shift, then the trick that everybody does is that you can write it as, let's see if there's a better chalk. So you can write it as e to the 2I delta Coulomb plus delta nuclear minus e to the 2I delta Coulomb, and then plus again e to the 2I delta Coulomb minus 1. So you just add and subtract the same quantity, which then leads you to the following, that this is e to the 2I delta nuclear minus 1 multiplied by the same phase shift for the Coulomb, 2I delta Coulomb, and then plus, this is just a Coulomb, e to the 2I delta Coulomb minus 1. Right, so you break this S minus 1 into two parts, this one and this one. This part is just a pure Coulomb part, and this one is a nuclear part multiplied by the Coulomb phase. So therefore your total scattering amplitude f of theta is given as, you have this expression, and in this expression this term is going to give me just pure Coulomb. When I sum everything up, it will give me only Coulomb. So therefore, I can say that this term is f of theta for Coulomb only. So this is sum of all these. Right? And then I have to add to that sum of all these, which is plus 1 over 2i k sum over L, 2L plus 1, PL, and then I can write it as e to the 2i delta nuclear minus 1 multiplied by e to the 2i delta Coulomb. Okay, so this way you actually broke your amplitude again into two components, just the Coulomb scattering, and this one you know analytically, this is simply a Rutherford scattering. And then in addition to that, you have an extra component, which is your nuclear component. So again, in all the codes, when you try to solve a scattering problem with Coulomb, then obviously you solve it relative to Coulomb functions. Solving it relative to Coulomb functions, the same equations that I gave you last time with Wronskian relation will give you delta nuclear. Right. Okay? So, by the way, I should emphasize that removing Coulomb wouldn't give you the same delta nuclear, right? You have to solve a complete problem with Coulomb. Okay, so when you solve it with Coulomb, that you obtain this set of coefficients delta nuclear, or phase shift for nuclear part, and then you can find the total scattering as just a combination of two, a scattering amplitude for Coulomb plus whatever you obtain for nuclear. And of course, when you square it to get a cross section, you get an interference. Okay, so this is just a brief summary of how do you deal with Coulomb. It's a very important question, and in fact, you also can obtain the rainbow phenomena that we have been discussing in the classical case, because this is the case where you do have Coulomb and nuclear, and you will have their interference here, which is a quantum mechanical effect. All right, so let me now show you, I think I have this, most of it in my notes. I have the Coulomb functions in my notes, the details. For example, this is the Coulomb amplitude. It's a lot of equations, but when you need it, you use it. Otherwise, it's important just to know how the process goes. Okay, so for, I think I had a picture. So this is the proton-proton scattering for very low energies. And then if you take very low energies and you only have the phase shift for 0, so this nuclear phase shift, delta nuclear, works only for partial wave 0, then final answer can be worked out. Everything. So in the cross section, when you square, of course you get a Coulomb cross section, which just gives you this term here. And then everything extra is this is your mainly interference term, and this is your term that gives you the sine square of delta 0 of the nuclear part. So, and this is the proton-proton scattering cross section. So if you look at it, this scattering cross-section, it's compared here with the dashed line, which is just a Coulomb cross-section. So at low angle, and by the way, this cross-section is symmetric. Why is it symmetric? With respect to 180 degrees. Identical particles again. So in addition to that, of course, this involves a statement about identity of particles. So this is a cross-section for identical particles plus nuclear and Coulomb. So everything put in together in one. And if you look here, at low angles, pretty much Coulomb dominates. Right? So, and then same happens at the high angle at about 180. In the middle, that's where you can learn about the nuclear-nucleon interaction from just this part. Again, if you do a full generalized analysis, which is also possible, then you can also generalize and obtain the scattering length and effective radius for this kind of scattering. Okay, so I think that's all I wanted to say about nucleon interaction, and what do we learn from reaction theory about nucleon-nucleon interaction, and also this concludes all the general ideas that one has to do in reaction physics to obtain cross sections. So next I would like to discuss with you, we'll come back to the question of the scattering matrix and discuss with you this issue: when is the cross section, or when can the cross section be infinite, and what are the singularities essentially in the scattering matrix. So let me go to this question. So if I have an S matrix, and as we talked, I have a solution which is U, and this solution U is essentially e to the minus ikr minus my S matrix, which depends on k, e to the ikr. So this is your incoming wave, is your outgoing wave. Okay, now if you would like to be more precise, I wrote it thinking of S wave pretty much here, but usually people would write this as a more general H, which is incoming function of X, and this, or R, or X if it's KR, and this is more generally some outgoing plus of X, right? So that would be a more general view. If you would like to keep, let's say, non-zero angular momentum, then these functions, or can be a lot of Hankel functions, or if you have exponents, then of course you know that H would be, in this case, let's say H minus is G, or H minus plus would be G minus plus IF, right? That's, and of course it's the same as e to the ikr equals to cosine kr plus minus I sine kr, and here is plus minus. All right, so that is sort of a generalized picture. And also there is minus 1 to the power of L, which I'm going to ignore here because it's not real. It's not going to change any picture. I just have to drag the extra minus sign. Okay, so this is my function u. And my Schrödinger equation contains only momentum k squared. So I would like to discuss this behavior of S as a function of k. Since it contains only k squared, and the solution here, which is a regular solution, is in some way unique solution up to normalization. So what happens if I change k to minus k? So if I take and change k to minus k. So if I do this change, physically in my Schrödinger equation nothing changes because it has k squared in it. So then I will have my new function u is going to be e to the ikr minus this s of minus k e to the minus ikr. So this is, let me just write it as u prime because, well, maybe prime is bad. Some other u, well, let me keep prime. It's not a derivative. It's just another function u where I change k to minus k. Now, this, if I take minus s of minus k outside, then this can be written as, again, e to the minus ikr, and here I would have minus 1 over s of minus k e to the ikr. Right? So just took this outside with a minus sign. Okay, but why did I take it outside? Because I know my u prime is, the solution is unique up to normalization. So this u prime is the same as u up to normalization, because Schrödinger equation doesn't depend on the sign of k. It's the same regular solution. So therefore, the only way I can make this happen is if this is u. So if this is u, that tells me that actually I have a property, and the property is that s of minus k, actually s of k, if I compare them, this one and that one, then s of k equals to 1 over s of minus k. Okay, so that is one property. So I have a reflection. If I change k to minus k, I get the same thing. Okay, so then another property that is useful to discuss is what happens if I try to extend this to a complex plane. So if I start thinking of my S matrix more generally, of course for scattering k is only real. But for the purposes of theoretical physics, we can still discuss k as being a complex number. So if I do a complex conjugation of my Schrödinger equation, nothing is changed again. So if at k real, I change my u to u star, so then nothing changes. What I will get is e to the I kr, doing a complex conjugation changes the sign, minus s conjugate of k e to the minus I kr. Okay, but again, from the same logic, it's a differential equation with the regular boundary condition at origin. I have to have exact same solution as before. So I'm going to repeat the same step again, and I will have here minus s star of k outside, and then inside I will have e to the minus I kr minus 1 over the s star of k so 1 minus s star of k e to the I kr. And this is this. Okay, so this is my new complex conjugated, but again it has to be the same. So again, this term is the same as my u. So what I will then learn is that on the real axis, my s of k equals to 1 over s star of k. But this is only if k is real. Right? So it's only true if k is real. Now what happens if I extend my k to a complex space? So this is known as analytic continuation. If the function, if a complex function, which is analytic, satisfies this quality on the real axis, then this equality to the whole space can be extended if I put here k star. Now I don't have to think about as k being real. It's valid for any k, and that is the analyticity property. Okay, so this tells me an additional fact now that I have another of reflection. If I change k star and as conjugate, then it's again inverse. Okay, so let's keep these properties in mind and consider first question. So what happens if I have s of minus I kappa? So now I'm taking k to be equal minus I kappa is 0. Well, I like 0 because then I go back to my wave function, and in my wave function u, I will have e to the minus I kappa r minus s of minus I kappa, which is of course 0, e to the I minus I kappa r. But this term is 0. So I only have this term. This term have minus I times minus I. It's the same as I times I, which is minus 1. So I will get e to the minus kappa r. Okay, so what kind, and now kappa is a real positive number that I'm thinking of. Okay, so this, what is this wave function? So what kind of wave function has an exponential decay? Far away. It's the wave function of the bound state. So therefore, what I learned from here is that if I think more generally about the S matrix, if I can just put any complex number for k inside my Schrodinger equation, then for a particular choice here, when I have a 0 here, then it's an exponentially decaying function. So if I were to draw this in the complex plane, then my picture would be as follows. So I will have my K space. So this point of 0 is somewhere here. So this is 0. Right? So therefore, because of symmetry, either one, if I change to minus, it's 1 over S. So there is a pole. And the pole I'm going to denote with this open. So it's symmetrically upwards. So then I have a pole on the upper plane. And that corresponds to bound state. So I can have many bound states. In that case, I would have more poles. It doesn't matter. So this is bound state. Okay, so furthermore, then of course in this case, through the residue theorem, my S at this point, at this complex point, I kappa, has to have a following form. It has to be some coefficient A over my, so let me see, let me write it, S of k around, so S of k when k is near this I kappa, so then it is k minus I kappa. So that way I will guarantee the pole that I'm looking at, right? Where A is some constant. So now I will leave it for you as an exercise, but you can show that if this wave function has here coefficient C, which is called an asymptotic normalization coefficient, then there is a relation between this A and the coefficient C, so which is A equals to I minus 1 to the power of L plus 1 times C, magnitude of C squared. And this is for a particular partial wave L. So we're talking about particular SL, obviously. Okay, so there is a relation between the residue at the pole for bound state and this normalization coefficient for the decaying state. We're talking about bound state, therefore the whole wave function u has to be normalized to 1 if we're dealing with the bound state. Okay, so next I have to discuss what happens or where else I could have poles or singularities. Yeah, I think it's actually a good moment to stop for 5 minutes, have a little break, and then I will continue. All right, so we're all back. Let us continue. So as I was saying, as a next step, I would like to discuss where else we could have singularities on this plane of the S matrix. So in order to do that, I would have to probably relate you to some physical ideas related to the properties of the S matrix when we talk about it. So I'm going to take a little digression and just relate this momentum k to the energy plane. So of course the similar picture, this is the k plane, but similar picture you can discuss. So this is the real and this is imaginary. But of course the same picture you can discuss in the complex plane. So suppose just for a moment that for some k which equals to k naught minus I kappa, where these are real and imaginary parts, we have a singularity. So then in the energy case, so the energy, which is a complex energy, which is h bar squared k squared over 2m, we are going to have h bar squared over 2m, and then here I will have k squared, and then which is k naught squared, so minus kappa squared, and we'll have minus 2 k naught kappa I multiplied by, again, this h squared over 2m. Okay, so this is the real number and this is the real number. So therefore, if I do this and I will write that my energy is some real energy minus I over 2 gamma, so which are real and imaginary parts. Okay, so that is the relation, and of course the relation here, if this is positive, then this is positive. And also the same here, there is a pretty much direct relation. Now, for discussing what happens with S of E, or complex E, just let me make it general. Let us try to go back again and to address the physics of the wave functions. And here an important statement is that the quantum mechanics is linear. So there is a linear relation between something that happens now to what was in the past. So the general theory that describes this is called the linear response theory. Now, it's somewhat still different. There are some differences between quantum mechanics and energy consideration, but let me talk a little bit more about this linear response theory. So let us think in the following way, that, let me just write it here, linear response theory. So let us think in the following way, that if I have my psi final at a certain time t, and we are talking about a linear situation, so this is a wave function, and there was some wave function in the past, and this wave function in the past, psi initial, or at some t naught, which is a past time. This affects what happens at the end, right? So you have to have a relation between your initial function and what happens at the end. So this relation is linear, and the only way to express it is to write this, or to define some evolution u of t minus t naught times this dt naught, right? So this is the most general relation between and linear relation between something that happens in the past and something that is now. And this kernel u tells me what contribution I have from each t naught going into the past. And this integral obviously goes from minus infinity up to a particular time t, up to my current time, right? So, and it cannot go in the future. All right, so this is the relation. And now trying to relate it to our S matrix, what I can talk is I can talk about energy representation. So again, I'm going to assume, which is not totally correct, and we'll discuss it later, I can assume that the energy varies from minus infinity to plus infinity, so there are no bounds. So then, of course, I can write my time-dependent wave function. Initial or final doesn't matter. It is an integral. It's a Fourier transform of psi final of energy. And then here I have e to the minus I e t dE. Right? So this is just from minus infinity to plus infinity in terms of energies. Right? So this is just our typical, if you have eigenstates in energy, this is how you would construct the time dependence through summation of the series or integration of the Fourier series. So then, of course, I have an inverse psi of final of E, which is 1 over 2 pi. If I define without anything here, then inverse has 2 pi. Then I have psi final of t, and then I will have here e to the plus I e t dt. Right? And I'm using units where h bar is 1 in this particular case, just to not write too many things. Okay, so this is my inverse, and then if I substitute this here, then I will have 1 over 2 pi, and then I have an integral. So this is also, every integral is from minus infinity to plus infinity here, unless marked independently. So it's e to the I e t dt, and then I have this psi of t, which is this one. So this is an integral of u of t minus t naught. And then I have here psi initial of t naught dt naught. Okay, so then one more thing I can note is that this u of t minus t naught, I can also write in the following form. I can say u of, actually what I can do is I can change variables and do this integration. Maybe that's easier. So I'm going to call this variable t minus t naught a variable tau. So I have to do an integration over t first, and then I will do an integration over t naught later. So dt is just d tau. Let me write it. I think I have very little space here. So psi f of t of e is going to be 1 over 2 pi, and then I have an integral here. First we'll do dt naught psi I of t naught, and then I have an integral over dt. So this is going to be an integral of d tau u of tau, and this one, so t obviously is tau plus t naught. So this one is just e to the I e tau times e to the I e t naught d tau. Okay, so now what you observe, of course, this e to the I t naught can be moved outside here. Then other terms is 1 over 2 pi, and then this integration here is just a Fourier transform backwards, similar to this one. So I will get my psi f of e equals to my integral dt naught psi I of t naught e to the I e t naught multiplied by u of e. So, and this is also a Fourier integral. So therefore, I get a standard convolution relation that, ignoring the factor of 2 pi, psi of e is actually this u of e multiplied by psi initial of e. Okay, so this is a standard convolution because I had this form, which I just wanted to show you. So, and you can think of this u of e as just being our S matrix, which relates our final and initial. Okay. Now, why I am talking about this is because there are particular properties of this u. Let me try to, I guess, erase some things. So, this u here is a special function that relates t to a previous time t naught. So this t naught must be in the past, therefore. So what we can say thus for u of tau is that if tau is negative, then it must be identically 0. So, and that is called the causality principle. So I do have to have a causality. Okay. So now how do we obtain this in the complex plane if I try to regain that? So my u of tau is an integral. Now I can extend from minus infinity to plus infinity. This u of e to the minus I e tau d e. Okay, so we are looking at this integral, and what I have to be sure is that if tau is negative, it doesn't work. It gives me 0. So now if I have this integral in the complex plane, again, so if this is my complex plane, I need to take this integral along the real axis. So this is my energy plane. So I need to take this integral, this is an integration from minus infinity along here. Okay. So now how do I need to close this integral? So I would like to take it by closing this integral somewhere, either up here, this is one option, or I'd like to close it down here. Coming back, this is my other option. Okay, so then it's a question, how is it going to behave? So let's say in this case, so here, if I have a pole, which is e minus I over 2 gamma, where gamma is positive, then I would plug it here, and I will obtain minus I, and then here I have e minus I gamma over 2 multiplied by tau. So this will lead me to, the real part gives me minus I e tau, which is not a problem, and the imaginary part is minus I times minus I, as we did before, gives me, so minus I times minus I is minus 1, so it gives me minus gamma over 2 tau. Okay, so it means that for tau positive and gamma positive, I'm okay because this far away in here, so if we are moving this far away, then the E and gamma go to far away numbers, then this is a converging exponent. So then this exponent goes to 0. So therefore, this means that for tau positive, I have to close counter this way. And then contribution from this counter is going to be 0 because it goes to 0. If tau is negative, then I have to close counter that way. Right? Okay, but we agreed that my integral has to be 0, my u is 0 if tau is negative. So it means if tau is negative, I close the counter this way, and the integral is 0. So using Cauchy's integration theorem, we infer that there are no poles, or there should not be any poles in this upper plane in order to satisfy this causality principle. Okay, so therefore all poles must be in the negative plane, in the negative energy plane. Moreover, of course, from here you learn a standard thing that you learn in usual textbooks, that if my psi final here has, so it has this behavior, which is as a function of time, it has this behavior as e to the u of e multiplied by psi of e, and then we're taking a Fourier transform of that e to the I, so this is my energy minus I e t dt, right? This is my Fourier transform of, this is equal to psi final of e. Then when I'm taking this integration, in this integration of energy, I have poles. And these poles coincide with the poles of u of e. And these poles are in the lower plane. So therefore, this integral just gives me a sum over all of these poles. Then, of course, there is 1 over 2 pi I, which I will just write as a coefficient r, multiplied by this exponent at the poles. So there is r for each pole. So suppose there are many poles, here, here, whatever. Then there are many poles, and for each pole I will have e to the minus I e pole t. So this is an oscillatory behavior multiplied by e to the minus gamma t over 2. So we learn that in this particular form, my final wave function as a function of time is a linear combination of decaying exponents. So, and each decaying exponent is given by the pole, by the gamma for each pole. So, of course, each pole has a different pole. Right? So, this is a very general conclusion. And as you see, I didn't have to do anything. What I have to apply, of course, is the causality principle that past must determine the future, not vice versa. So, therefore, if you go back into here, into K-plane, and if you extrapolate or think of this U as S matrix, which is pretty much what it is, if you have in the energy representation, then you obtain that the poles, of course, in the complex K-plane have to be in here. So there should be somewhere poles. I'm drawing poles as open circles here. So there should be somewhere poles in this quadrant to assure that you have corresponding resonances in energy. Okay, so sorry? Gamma can also be 0 for a bound state, but this is this one. Right, so this is a pole on this axis, which we already discussed. Okay, so far I'm only talking, of course, about the poles which I encounter in this complex plane. Okay, so that proves, of course, that I have to have poles in here. So now we can discuss absolutely general properties of the S matrix. So what happens if I am near a pole? And as we already kind of know from the S-wave scattering, that near a pole, my cross-section is large. Okay, so what if I'm near the pole? So suppose I have S matrix of K near the pole. So then I have S matrix, I can write it as being proportional, let's say, to 1 over K minus K pole. Okay, but we know that, of course, I have S of minus K equals 1 over S of K. So therefore, I actually have to say that because of that condition, a more general form would be K plus K pole over K minus K pole, to be correct. Okay, so then there is another condition, is that S of K equals to 1 over S star of K star. So therefore, of course, I have to do even more. I have to say that this is K actually is proportional to K plus K pole. Then I have to take star of that, K minus K pole star divided by K minus K pole multiplied by K plus K pole star. So this is the form that my S matrix have to have near a pole given all other considerations. Okay, so and you can actually notice here an interesting thing, that if I complex conjugate the numerator, I get the denominator. Okay, so therefore, in fact, this is a unitary number, actually. So the magnitude of it squared is as 1, because complex conjugating numerator gives me a denominator, right? So the numerator is a complex conjugated denominator, so the magnitudes are the same. So therefore, I already learned that even in this form, the magnitude of this is 1. So therefore, in general, which I'm not going to discuss, people usually write this way, that they say, in addition to that, this is 1, but most general form has an extra phase shift, some kind of 2I psi. So where psi is just some other constant, which we call often a potential phase shift. Okay, so and in this, as I was saying, this modulus of S of K squared is 1. Okay, I'm not going to deal with this phase because it's not really important. It just gives an extra interference, but I will discuss what happens here. So as I said, K pole must be some K naught minus I kappa. So therefore, if I write the numerator, then in the numerator I have K plus K naught minus I kappa multiplied by K minus K naught, and then I have minus I kappa again, right? So this is just the numerator of this. Okay, so if I square it, what I have here for the real part is I have K, so this is plus and minus, so I have K squared minus K naught squared minus kappa squared. And then for imaginary part, I will have minus I kappa multiplied by k plus k naught plus k minus k naught. So this is just the numerator. So if we look at the square, and of course the denominator is just a complex conjugate of that, so I'm not writing the denominator. So this is proportional, so k squared is proportional to my energy. So this is essentially proportional to my energy. This quantity, according to that, is proportional, so this is a scattering energy. Right? So if I were to write S of E, that's what I'm trying to write. This E is just my scattering energy. This is the energy of the pole, which I will write as E equals E, let's put naught, and then have a complex part which is gamma. So this is going to be E naught, and this part is related to I gamma over 2. Right? So now putting everything together, there is a common factor h bar squared over 2m. Then I will have here as my scattering energy minus E for the E naught for the pole that I was denoting, and then minus I gamma over 2. So if I call this times this quantity h bar over 2m, if I call this gamma over 2. So I'm just going to define this. And then the numerator is, or denominator is just a complex conjugate of that. Okay, so of course in this discussion there is one more consideration, that we always talk about kappa being rather small. So kappa is much smaller than k naught in this particular form. So that way I can associate this, this is my energy, this is again my E naught, and this part I will define as gamma over 2. And this part is negative here, and complex conjugation in the denominator gives me positive. Okay, so this is now in terms of the energy representation, my general form of the S matrix. Okay, so then having this form of the S matrix, we can go back and compute what is the scattering amplitude, or scattering cross-section. So for the scattering cross-section, actually maybe since I'm showing this, before I talk about scattering cross-section, I have to show you this picture. So this is the picture of the poles in the complex plane, and you can see, as I was showing, these are bound states, then these are resonances. And of course, if states are very close to real axis, that's the most interesting case. If gamma is small, then the states are close to real axis, and they would be narrow resonances because they're decaying their, which I raised, the exponential decay of the wave function would be very slow. Now you can have very big gammas, so, and then these are broad resonances. So these states decay so fast that you don't see anything. Okay. All right, so this is a general picture. Maybe I should also mention there is a lot of work in theory trying to study the structure and reactions using wave functions in the complex plane. So, for example, you know that there is a set of wave functions on the real axis. So if you take all your all kinds of values of k in the real axis, then these wave functions will form you a complete set. So it means that any wave function can be described in those basis states. So these would be a complete set of bases for real energy. Now, it may be convenient to consider a complete set of states where you have complex energies. So this complete set of states can be formed by looking individually at resonances plus all states along a certain arbitrary contour line. Right? So let's say you take this contour line, you take all possible values of k, so you make all possible u of k for this contour, and in addition to that you take these two, and that will provide you also with a complete set of states. So this complete set of states allows you to build what's called a gamma approach, and if we will discuss maybe a little bit later about the many-body formalism, where using a nuclear shell model is a very common approach where you construct from Slater determinants many-body configurations. So these Slater determinants are some basis states, and they can be arbitrary basis states. Usually these states are picked as harmonic oscillator states. But if you are dealing with the problem with continuum, you may want to solve your realistic potential completely correctly, such as Wood-Saxon potential that I was discussing earlier. This Wood-Saxon potential would provide you a complete set of basis states, which include bound states, and it includes continuum states. The continuum states you can take on the real axis only, which we usually do in quantum mechanics. But to be better, you can actually take a continuum set of states along the contour. So you'll take two bound states in this example, two resonances, and then the continuum set of states along the contour. And the hope is that, of course, resonances and the bound state would contribute the most to your physics of interest, whereas this contour may be less important. Okay, so that's some digression related to this picture. So now if I would like to look at the scattering cross-section, which I started doing, and I don't think I need this anymore. We all remember it, and it's on the board. So then I have my cross-section sigma is just pi over k squared, and then the magnitude of s minus 1 squared. So if I have this s minus 1, so my s is e minus e naught minus I over 2 gamma over E minus E naught plus I over 2 gamma. By the way, of course, if you associate this with a complex energy, then complex energy is E naught minus I over 2 gamma. So you correctly have or you satisfy all that discussion about causality and that the imaginary part is negative. So have this minus 1, and this is what I want. So then you add this in the, you bring them on the common denominator, which will give you E minus E naught plus I over 2 gamma. And in here, the real part will cancel, but the imaginary part that has opposite sign will give you minus I gamma. Okay, so therefore, when I go to a cross-section, I have to take the magnitude of this complex number. So, and the magnitude of this complex number is simply magnitude of the numerator, which is purely imaginary. And then this is contains real and imaginary parts. So this is pi over k squared, and then here you have gamma squared over so we have a real part squared, E minus E naught squared, plus the imaginary part squared, gamma squared over 4. Okay, so this is called the Bright-Wigner form for the resonance. So it shows you the cross-section that has a peak so the picture, pictorially, if I were to show it, then pictorially you have a cross-section, and this cross-section will have a sharp peak. Okay, so this Bright-Wigner form, assuming gamma is constant, is actually a symmetric peak, right? So which I'll try to draw here. I guess my symmetry. Okay, so this is a typical resonance. Now, if you would like to compute the width of the resonance, then there are many options. So one option is, of course, then if you're looking at the phase shift, so if you know how to do the phase shifts and you'd like to analyze the lifetime, then you can relate this to your phase shift. So if this is your S matrix, then this S matrix equals to e to the 2I delta, right? So this is a complex number in the numerator, and the denominator is a complex number. So, and they're complex conjugate of each other. So the numerator has some magnitude and the phase, and the denominator has some magnitude and the opposite phase, and the minus phase. So therefore, if you think of a numerator, the numerator has to have some magnitude m multiplied by the phase, and the phase actually has to be I delta, because then the denominator has a magnitude m, and the magnitude, of course, doesn't change in the complex conjugations, times the phase minus I delta, right? So that way m cancels out and you get what you want. Okay, so therefore it's straightforward to get the delta. So delta is just the argument of this complex number. So, and the argument of this complex number is, we can use the tangent, for example. So it's a minus arc tangent of gamma over 2 over the real part, which is the energy, E minus E naught. Okay, so that's the phase shift that you get. Then if you would like to actually measure, then clearly what kind of options do you have for deducing the resonance width? So if you are doing practical calculations, and in your calculations, in one of your homework assignments, you have an example where you can try all the methods, so which is a delta function confining barrier. So you have a delta function in the radial direction, and you can solve it. You have many options. So that problem you can solve almost analytically. So, and in that case, you can obtain S matrix in the explicit form, and looking at the poles of the S matrix, you can find their real and imaginary parts, and that way you'll obtain the width. Now, sometimes if you are doing actual scattering, let's say in experiment, you don't have access to imaginary axis. So in experiment, you can only manipulate with your energy of the beam. So it's only real part. So therefore, you're looking at the phase shift on the real part, where k is real. So this phase shift, let's say if you take this phase shift has this behavior, which I think I had a, so if, yeah, okay, well this phase shift, so this is the Bright-Wigner shape, and this is how the phase shift is going to look like. It's a sharply increasing function near the resonance. So this phase shift, if you take the derivative of the phase shift versus the energy, so let's write it as a function of energy here, d over dE. So actually phase shift is d over dE of 1 over 2I log of s, right? This comes from here. So, and then this is 1 over 2I derivative 1 over s d over dE of s. Okay, so, and then I can substitute 1 over 2I. So 1 over s comes from there, so it's E minus E naught plus I over 2 gamma, right, by E minus E naught minus I over 2 gamma. And then the derivative of course, from here you see that I obtained s minus 1 is this term. So if the derivative of 1 is 0, so I can just take the derivative of that expression. So, and the derivative of that expression is, so let me make sure that, so this is s minus 1, so the derivative of that expression is minus I gamma, and then there is an extra minus sign because this is 1 over x derivative, and then the denominator squared. So this is e minus e naught plus I over 2 gamma squared. Right, so this is the full derivative, then this square cancels out, and minus minus disappear, I cancel out, so what I will get is that this is just gamma divided by 2, and this is a product of two conjugate numbers, so this is just e minus e naught squared plus gamma squared over 4. So if you look at the phase shift exactly at the resonance, so d over dE of delta of E exactly at E resonance, or E naught, at E equals to E naught, then what I will have, this term disappears. I have gamma squared, 1 gamma cancels out, and then there is 1 factor of 2 left. So this is just 2 over gamma. Okay, so again, this is a relatively famous expression, and this is one way how you can find numerically, let's say, if you're interested in the resonance width, then you locate your resonance, and you can locate your resonance by maximum in the cross section. And I'm not going to work it out, but also at the resonance, the second derivative of the phase shift is 0. Okay, so you can work it out, and then you can find the first derivative, which gives you width. Okay, so you first locate the position of the resonance by, let's say, maximum of the cross section, and then you look at the derivative of the phase shift at that moment, and you obtain this. There. That's yes. In fact, in your original plot, you had two resonances, I think, in that test matrix you showed. The first thing you showed today, in which you had the real and imaginary part of the S matrix. Which one? The first picture you showed today. Oh, okay. Yeah, it's far back, but anyway, I can show it again. This one. Okay, well, I don't know about these I can check, obviously, about the resonances. Here I was just showing everything. Okay, so anyway, there are other ways, in fact. So there are several other ways, and actually there is another way is if your resonance is very narrow, then it may be difficult to solve it on a complex plane using complex numbers. And that often happens, for example, if you're discussing alpha decay or proton emitters, then their widths can be 10 to the minus 15 and so on, MeV. So it's orders of magnitude smaller than the real parts. So there is no way computationally you can handle these small numbers. However, there is a straightforward way in that case, because you can solve the problem as a real problem on the real axis. And you can ignore that complex part. You can normalize your wave function as a stationary normal wave function to 1, and then try to extract the outgoing flux. So in the wave function, as I was alluding earlier, you have incoming wave and outgoing wave. So your U still has e to the ikr, which incoming, and then a minus S matrix e to the ikr outgoing. So you, in the normalized wave function, you'll try to extract this part with the Wronskian relation, which again not gonna spend time on details here, but this is a straightforward process. So you obtain the outgoing part, and then you can just simply say, I have a frozen wave function where I ignore the decay because it's so slow, but it still has to have some outgoing component. So when you extract with the Wronskian this outgoing component, that gives you an outgoing flux. And once you have an outgoing flux, you know the decay rate. So, and from a decay rate, of course, you do know the width. Okay, that's another option. And then perhaps there is a third option, which is the Fermi-Golden rule, which is also straightforward. You solve your problem as a real problem, and as we were discussing earlier, you can immediately apply a Fermi-Golden rule and compute the overlap between your scattered state, which you know, and your bound state. And in the middle, you have your potential. So once you take this overlap, it also gives you another way of computing the width. So there are many ways of doing these kind of problems, but of course all of them assume that the width is relatively small. So you do, I mean, it's a kind of assumption that it makes physical sense to look at the width if it's relatively small. Okay, so let me see. I guess I discussed this. What I also wanted to discuss with you, let me see, which is mainly, well, I have some pictures, of course, showing the poles and showing the resonances. If you'd like to see, maybe we'll post them later, some of my slides. This is the picture of poles in the square well, and this is also a picture how the poles evolve if you change the size of the well. So it's just basically real and imaginary parts, and you change the depth of the well, and each time you change it, you put a point. So this is like an evolution of poles, and they come from here, and then they drop, become bound states. Of course, here I reflect them. Actually, the bound states go up, but I reflect them down. So they say this one goes here and then drops down. So this is an evolution of poles as you change the depth of your potential. So in the remaining time, I wanted to discuss this interesting problem with you, physics of decay and instability. So now I'd like to address the physics of decay from a time-dependent perspective. And this is a very old problem. So in fact, it dates back to Zeno paradox of arrow, that if you look at your time evolution of an arrow, then there's no evolution, assuming you say, well, each moment of time is instantaneous picture. So the way, of course, this is resolved is if you have calculus, right? Calculus allows you. Now, the question of time evolution, whether it's exponential or not, which I was just proving, is more closely related to a Zeno paradox, right? So I showed you in my simplified picture that the evolution of a state in this S-matrix picture is exponential, right? But it cannot really be exponential. And this is another point. If you have a quantum mechanics and you let your state be, and then you like open pot all the time, so you have to reset your state. So each time you reset your state, you do something to your decay. So it is a question of your measurement. How does it affect your actual decay? And there's been a lot of discussion about it in the literature. Okay, so then finally, there is another important component that I have to mention, is that even classically, it was noted that the decay at remote times definitely cannot be exponential. So you can, I think I had some examples. Well, let me mention another quantum mechanical example, is that, of course, in quantum world, the decay definitely cannot be exponential. And there are various arguments for that, which I'll give later. Okay, so also related to recent literature, there's been interesting discussion about this GSI mystery, where you have a exponential decay law would be this red line, but what is observed or believed to be observed is this dashed line. So there is a oscillation in the decay curve as opposed to exponent. And then another interesting story is related to this problem with the beta decay because it's related to carbon dating that everybody uses or many people use. And if it is not exponential, then maybe there is some kind of issue. So now let me try to explain to you why do we believe it is exponential and why it cannot be exponential. So from classical perspective, the exponentiality comes trivially because from classical perspective, we just say, well, we have some number of samples and the rate with which these samples disappear is proportional to the number of samples. The only solution, therefore, is exponential. Now, in quantum mechanics, we have an evolution, which we were just discussing. So where h is your Hamiltonian operator, and this is your wave function of time. So you can discuss the decay amplitude with this. And there's also an exercise in your homework. You can almost immediately show that this cannot be exponential. Now, if you do a time transformation, which we were discussing, energy time transformation, which is a Fourier transformation, so this is a, then in the energy spectrum, you get this Lorentzian, which I was just deriving you. Okay. So, but this Lorentzian, what we were discussing, implies that this Lorentzian is completely symmetric, right? But there is some energy cutoff. So the Lorentzian cannot be symmetric. So it has to have some kind of cutoff here. So therefore, it cannot be exponential, at least in that relation to cutoff. Okay. Okay, so this is the discussion. At early times, we can expand it. And this has to be a power law if we expand this evolution operator. Then at the middle times, we have a cutoff, so we have a problem here. So if the particle decays, you don't have a Lorentzian, you have to cut it. So therefore, you don't have exactly this shape, but you have a modified shape. And then at remote times, you have a power law, as I was saying. And now I can give you this classical argument, which is not really correct, but it's still a good argument. So suppose you have a box, and suppose you put in a particle in there. So this particle has extremely low energy. It's almost not moving. So if this particle has an extremely low energy, then the number of particles in the box as a function of time, you can estimate as the size of the box divided by the velocity of the particle divided by the time, right? So this is how many escape. Then you can do an uncertainty principle and change this delta x to h bar over mv squared. And then mv squared relates to your energy, so this is just 2h bar over energy time. So, and of course, number of particles proportional to your wave function squared. So for these slow particles, therefore, you learn that classically you would expect the long times that the decay or the number of particles goes as 1 over t. Right? So it's not exponential. Now, you can do these estimates, how bad are these problems for, let's say, carbon dating, and you learn that they're not really bad. So the initial time, or the slow time, you can estimate the first time or the second time where you cut off your exponent, so you can estimate from how far your Lorentzian has to end. So this is from the excitation energy, of your state, ratio to the decay width. And you find that the problem only occurs at the level of, at the timing 10 to the minus 21 seconds, right? So for carbon dating, that's really completely useless or unimportant because it's such a short time that you don't really worry about it. So at this short time, the decay is not exponential. Now, at the long time, the last time, which is related to this one, you can estimate it according to this equation. You can estimate this E naught over gamma, and you find that this is essentially 73 lifetimes. So if you go more than 73 half-lives or lifetimes, then again, decay can become non-exponential. But if you take 2 to the power of minus 73, you find a ridiculously small number. So it means at that level, the amount of sample is so low that you don't really see it. Okay, so now I would like to demonstrate you. So in your homework, you have an exercise where you have to find resonances in the S wave in the so-called spherical shell delta potential. So your S wave potential radial part, so this is R, this is U of R. So it's an S wave, so it has a delta function here, right? And it has, this delta function has some strength, so the G times delta of some value R minus capital R. So, and this is the potential that I'm considering here. So you can do all the solution and all the discussion analytically what we have done. What I would like to look is how does this, how does the state in this potential evolve with time? Naturally, if this delta potential is very high, then you essentially separate the spaces, outer space and inner space. Then you have a bound state in the inner space. It's a completely separate from the outside. And for particle in the box, the solution is just a sign. So the lowest solution is simply so the lowest wave function is simply going to be a sign state. So I'm going to take this sign state here, which shows the density of it, and I'm going to let it evolve with time. So what's shown here is the current as a function of x, and the current we discussed in the first lecture, which is just J, but as a function of x. So I'm going to put anything here and measure here J of x, which is, in that case, x is the R. Okay, so my potential here is my delta is at 1, although sorry, it's drawn here at 0, but it's at the position R equals to 1. And this is the density in the momentum space. So this is a Fourier transform. So if I'm going to look at it, then this is the time evolution. So this is how my state evolves with time. And you see some moment, initial moment, it shakes a lot, and then it becomes rather stationary, right? So it almost continuously decays. All right, so then there is an interesting phenomena that you have this kind of shoulder forming, and this moves. Okay, so and then I can also show you, this is at initial time, that survival probability as a function of time. So this survival probability as a function of time, the dotted line shows the exponential behavior, and the red line shows the actual behavior, which is computed numerically here. Right, so, and you see there is, first of all, in here, it starts quadratically in time, which is your homework exercise, so somewhere very here. And then it still oscillates a little bit, and then it moves on to a longer time, and this is the next question. What happens at the longer time? So this is, if you saw here, this, I'm sorry, yeah, it erased it, but this started at the later moment, and this I'm going to start at the moment t.5. So I magnify this picture, the top one especially. So this is a formation of that shoulder that I was mentioning. So if I take this shoulder and continue it, then you see that this is my resonance which stays, and then there is what we call a background, that kind of a flush that moves away. So schematically you can see this picture here. So this is my resonance that leaves, and then there are background particles that move away. Okay, so and then I can show you what happens with the survival probability far in time. So, and this is my survival probability. At first I was showing you earlier times, very short times here. There were some small deviations that we saw. And now this is on the longer time scale. So what I have now is I have a combination of two components. One is my resonance state, and the other one is my what I call background. These are very, very slow particles that I was discussing with you earlier in the classical example. So then in quantum mechanics, of course, this decays exponentially, but this decays as power law. So it goes as 1 over time to some power. So it decays much slower. And because this decays much slower, at some moment, this background wins. And this is your survival probability. And this shows you exponential decay. But at this moment, these two amplitudes start to interfere. And then it transitions to this power law, which is 1 over time cubed behavior. Okay, so this is the result. Then I think I have some other. We can start from the second excited state. So here I started from the first just a sign, but you can start with one node wave function. So there's a one node wave function. That would be a second excited state. So if I start here, then I have several transitions. I have a fast decay, which corresponds to one pole. Then I have a slower decay. So one pole is completely exhausted. Then I transition to a second pole. And then I have a power law. Okay, so now if you work this example, I don't have enough time to discuss it completely. So if you work out this example, then everything here is pretty much analytic, and this is actually known as Winter's model of decay, which shows that the decay is a power law. So, but let me briefly give you, it's the moment. I'm just gonna briefly tell what happens and we're done. Okay, so first you need all states. Let me label them as K. So you need all eigenstates. So these eigenstates remotely are just sine of kr plus delta. So, and the delta depends on k, obviously, and that's what you have to find. In fact, normalization, I also know. The normalization here has to be 2 over pi. With this normalizations, my states, k prime, are going to be normalized by a delta function of k minus k prime. And that's always like that. And you can show it by looking at the exponents and by looking at the delta function, which I discussed with you in the first lecture. Okay, so then in order to find your time dependence, so if you would like to, if you have some initial function psi, so then, let me write it this way. So if you have survival probability, or survival amplitude A, is essentially your overlap psi of t times psi of 0. So, and this is the same as psi of 0 times e to the minus I h t psi of 0. All right, so you can do this analytically in this problem if you have A equals, so if you insert here a complete set of basis states, and these are eigenstates. So this becomes an integral. Here you have A k, and this is multiplied by e to the minus I k squared t, and this is squared d k, right? So what I did here for quickness, I just took that my h equals to k squared without anything, and my, this a is psi of 0. Okay, so this is my expression, and what you have to do is you have to take this integral in here from 0 to infinity. Okay, and then you have to start discussing how do you take this integral, and you can take this integral in the complex plane, and in the complex plane we're only talking about negative part, so this is a k dimension, so you have to take it along this line. And unlike the unitarity problem that I was discussing, here you only have half the plane because your energy is half, and your energy is cut off, and that's always the problem. So all this power law comes from the energy cutoff, so there is a lowest energy that you can have in the problem. So I was taking previously energy from minus infinity to plus infinity, which is not physical. So here there is the lowest energy. Assuming there are no bound states, you would have to, you take this integral, but you can complete the circle. And in order to make this Gaussian integral, you actually can complete it up to here. Then this component gives you 0. This component along this line is an integration which contains a real Gaussian. So k squared along this, ik squared along this line is a real number, a negative number. So this gives you some Gaussian integral, and then there are poles inside, which you can find. So at the end, your answer for this A is going to be this part of the Gaussian integral, which is proportional to, in fact, 1 over t power of 3 halves, plus pole components. So pole components, as before, give you decaying exponents. This one gives you an exponential background, or the power law background, which is that outgoing background. All right, so I think maybe next time I'll mention a few words about this problem, because it turns out that this background is related to our S-wave low energy scattering, because we're talking about very slow particles, and we discussed our scattering length for very slow particles and the behavior at very low energies. So in fact, this power law is directly related to that behavior. All right, so I'm going to finish now.